Alright, so I wanted to start the first video of figuring out the structure of the wing. I found some actuator companies that I think have some pretty good products that I'll be able to go ahead and make the first version active. That's cool. I'm looking forward to doing that because the actuators are small enough to where before I get them working with the electronics, I can just use them as structural components. I can get the wing on there, installed and functional, and leave it on until I get it the active portion working. So I'm gonna do some 3D scanning right now. I already got one 3D scan. I was trying to figure out where I was going to mount the wing brackets. And there's a lot of structure under here. I'm not gonna take this off right now because I've taken it on and off like 20 times. But if you have an 86, you know that there's like a bunch of stuff that goes across here. And she's put on so much weight. Do you remember in previous videos, she was so skinny. She got down to 45 pounds. She's over 65 pounds now. I'm so happy. You're healthy now, baby. You're a healthy weight. Yes, you are. Yes, you are. Yes, you are. Anyway. So shout out for Amicia. What was I saying? Oh yeah. So I wanted to see if there was a way to mount the wing without permanently altering the trunk. So it's a bit of a stretch goal, but I saw these brackets here and I thought it would be super cool to be able to mount it between this bracket and this nut and then just have a piece come around here and come up and serve as the mounting point. For now, all I'm going to try to do is 3D scan this area right here and model up a test piece that will mount under these nuts on top of this bracket. So on this side of the bracket, so it doesn't affect the dimensions on how the trunk mounts and mates with the rest of the car. I'm going to see if I can test print something that will come over here and just loop through. I'll probably have it stick up a centimeter or something past this just to test the tolerances of where the panel gap is. So that will have to be extremely precise since the force won't be constant. There will be a lot of wiggling around. So that's my current objective. So we're gonna do that. I'm gonna go ahead and plug in the 3D scanner and we'll get that done. Baby, just lay down here in the shade or something. Why are you sitting over there? If I touch your fur, I bet it's gonna be... Oh my God, I don't know how you do that. What are you doing that for? Don't look at me like that. I just care for you. Okay, so super hot out there. Got a shower. I'm going to pull up the scan. Actually, I need to process the scans. Then I'm going to pull them up in Fusion 360. So let me get on that. So we got the point fields from the scans combined, and then we got it meshed. Now I'm going to import it into Fusion, see if we can clean a few things up, and go from there. Okay, designed a little bolt hole tester thing. We'll see, just to make sure the 3D scan is dimensionally accurate. I'll throw it on the trunk bolt mount thingies, and we'll go from there. Okay. Hey, baby. We got the dimension test thingy. Now we're just gonna slide it on here. Ooh, almost perfect. It's a little snug. Ugh. Maybe 1 more millimeter. So this is really close. I would give it maybe 1 more mil, see if that works, and then compare that to the 3D scan, and then modify the scale of the 3D scan to make sure that the one we make fits this, and we should be good to go. All right, so I 3D modeled a test piece from the 3D scan of the trunk. I made a negative to make sure that my scan was scaled appropriately once I put it into Fusion 360, or after I put it into Fusion 360 rather. So I made this. Let's see, it goes, there it is, yeah. Nice, okay. So that fits really well. So I think we got our 3D scan pretty spot on. Very good. So now I just need to figure out the dimension to get this to loop around here. And then this will be fairly easy to attach it to this. I just need to raise the surface up to this bracket level and then make those holes. And then for this, what I can try to do is cut this surface up to a few millimeters of this surface, and then add that flange for the bolt holes. And then I don't know what I'm gonna do to figure out how to get it exactly with this edge. I might try to expand this out a little bit, because 3D scanning this edge is really difficult. Just getting that edge, because there's not much reference to get that edge. I'll figure something out though. Might have to get creative, but that's what this whole process is about, right? So 3D scan is good. And now we're going to expand this part to see if we can get it to mount here and basically come up with something like this, but that's just a few millimeters thick and that mounts on these bolts, and we'll attach it here. If that works, then I'll make a mirror for this side and we'll attach it here and make sure that works, to make sure it's just, you know, a mirror like what we're expecting. I really hope it is a mirror. If it isn't, that's gonna suck. All right, so I've printed this template that's going to go on the trunk bracket. I'm gonna take the bolts off, slide these onto the bolt areas, and then this surface is going to fit like that last template I made, hopefully. But right now, I'm gonna make sure that this fits. Already ran into a problem. This is going on like this, but that's in the way. So I need to trim some off right here. So let's go grab the Dremel. This is probably overkill, but it's just what I have right now, so. I'd say that's pretty good. It is right there. Very nice. Okay, perfect. That is pretty solid. I think we've got our template. We got it, boys. Let's go ahead and put these nuts back on. Or take this off, put these nuts back on, and we'll hop back in Fusion 360. All right, let's look over some stress calculations that I did for the bracket. I wanted to do some hand calculations just to see if the carbon fiber bracket that I'm planning on making is even close to being strong enough. So I had to break out the ancient tomes. The way I calculated the stress for this is I used the worst case scenario. That is 150 miles per hour with the maximum coefficient of lift and the maximum coefficient of drag. Those do not occur at the same time. The maximum coefficient of lift happens about 9 degrees angle of attack, and the maximum coefficient of drag happens about 30 degrees angle of attack. So I'm using worst case scenario from both, combining those and using that for getting the total value of the force on the airfoil. The only thing that I didn't do worst case scenario is I used a 5-inch airfoil instead of an 8-inch. I have a table for 5, 6, 7, and 8-inch airfoils, the basically Reynolds number for those across 0 to 150 miles an hour in 5-mile-an-hour increments. I don't know why I use the 5-inch airfoil, but after you get the coefficient of lift, the force scales fairly linearly. So I can scale it about 60% to get what the forces will be on an 8-inch airfoil. The reason I'm doing these stress calculations now is because I want to be able to see how I need to build the bracket, number one, and number two, how much force I can get from my airfoil. So if I have a large margin of strength with a 5-inch airfoil, maybe I can bump it to 6 inches, get more downforce, see if these brackets will hold up with the geometry that I'm planning on using. So let's go ahead and look at these calculations I did using 150 miles an hour, maximum coefficient of lift, maximum coefficient of drag with a 5-inch airfoil. I'm going to skip through all this. If you guys want to go into more detail, let me know. But basically, I just calculated the area of the 5-inch chord length airfoil with a 58-inch width. I got the maximum stress lift, maximum stress downforce, or drag, sorry. And then I made a free body diagram, a little bit of trig, gave me 1,464 newtons. And so then to get the amount of stress on each side, all right, divided by 2 to get each side, and then to find the difference on the front mount and rear mount, what I did was I used the coefficient of drag to see how much force is, like bending force, is going to be on the mounts. And so the drag is going to add to the force on the rear mount, and it's going to reduce the amount of force on the front mount. And so that ended up being about 85 pounds for the rear mount and 76 pounds for the front mount. And that is with an 8-inch mounting height, so approximately 0.2 meters. That force will get more and more different between the front and rear mounts if you increase the mounting height. So your rear mount is going to be basically your weakest point. And that's not including the force from the actuators during transients. So while the actuator is pushing the airfoil up, that stress will likely be higher depending on what the rotational point is on the airfoil. So since I'm planning on making a curved airfoil, some of that aerodynamic force is going to be in front of the pivot point and some will be behind the pivot point. And I'm going to try to balance that to make sure the actuator needs to output as little force as possible. So if that is balanced, the force on the back and the front of the airfoil should cancel out and reduce the amount of stress on the actuator by quite a bit. So we have about 161 pounds per side. That's going to be the stress on each one of those mounting points. Whoops. Calculating the deflection, I had some trouble doing this for carbon fiber. It's really tricky because it's a composite material. A lot of different things going on with composites, but it has a flexural modulus of 56 gigapascals. I calculated that, and that had an extremely small deflection. It didn't really make sense for a 2 millimeter thick carbon fiber part with 160 pounds on it. I just couldn't imagine it being that small. So I went with the tensile strength. So while I'm editing this, I realized the flexural modulus is more closely related to the modulus of elasticity. So I think I should use the flexural modulus. However, the deflection given by using that number seems extremely low. If any of you know what the proper modulus is for carbon fiber, specifically 2x2 twill with common epoxy resins, please let me know. Until I have a better number to use or I figure this out, I'm just going to keep using these calculations for better or worse. But I plan on coming back to revise these numbers at some point. So just a quick editor's note. I used that instead. It's 552 megapascals. And that gave me a much more reasonable deflection. I used 10 centimeters as the cantilever distance where the force is being applied, because that's about the distance of the bolts underneath the trunk to the edge of the trunk. That's where it'll be supported. So I got a deflection of approximately 4.5 millimeters, which makes way more sense. I feel like that's still kind of small though. So maybe we're being a bit conservative here. Then I got an idea of putting riv nuts along this area of the trunk because it's flat. It is outside the weather ceiling, and there's already other holes out here that on the bottom of the trunk that aren't sealed. So I don't think it'll be an issue with, I don't think it'll be a problem with water ingress or anything like that. I'll probably go ahead and still seal them to just try to make sure, you know, nothing gets in there that shouldn't. But if we put riv nuts here, that reduces the cantilever distance by about half. And the farther out, you know, that you go on a cantilever beam, the deflection increases by, I believe it's a power of 3. So using this distance from these riv nuts instead of the distance from these bolts, you have a much more reduced deflection, and calculated out, that comes out to about 1/2 millimeter. So that's pretty good. Really good reduction, and if you use both of these, that'll increase the rigidity even more. And we can keep the thickness of the carbon fiber under this area much thicker than what's coming up through here. So the deflection of the carbon fiber piece underneath the trunk is going to come from a flat piece of carbon fiber bending like this. But the carbon fiber that comes up through that panel gap, all the stress is going to be down like this. So we can get away with a thinner piece of carbon fiber right here because all that bending is going to be in the carbon fiber panel, I guess, underneath the trunk. So we can keep this a bit thicker than 2 millimeters. Could even go 5 millimeters, make it ridiculously chunky. But so I think we're looking good as far as stresses go here. We can thicken it up, and we can add another piece on top of the trunk. So this is looking from the back forward. These are these bolts that are going to go in where the trunk mounts to the bracket. These are where those riv nuts are. And then this yellow piece is the cantilever piece right here. And this yellow part coming up, that's the vertical part coming up through the panel gap. And then if you have a second part right here that actually grips the actuators, we can put a little bit of neoprene foam and some PPF right here so it rests on the top of the trunk, and that'll absorb a lot of that force that the wing is generating. So you won't get all that force being transmitted through this cantilever part right here, and a lot of that force will be absorbed by the edge of the trunk. So I think we're doing a pretty good job distributing the force to multiple points. Not only that, the deflection that I measured was a perfectly flat rectangular beam. This will be off axis a little bit from how the bending force is applied. And not only will it be off axis a little bit, it will also be curved a tiny bit. Both of those things increase the stiffness quite a bit. So using 150 miles an hour, maximum CL and CD, calculating deflection using a simple rectangular beam instead of this curved off-axis beam, reducing the cantilever distance, all those things add up to better than what we're calculating. So basically we're calculating an absolute worst case scenario, and we already have a lot of factors that are going to be better than worst case scenario. I don't even think the GR86 goes up to 150. I think it tops out at like 130. So overall, I think we're in pretty good shape here. I'm going to keep working on the carbon fiber mold for this yellow section here, this bracket, and then I'm going to try to 3D print another template that includes this vertical part here. This will take some fitting and trial and error because this part of the trunk on this edge is very difficult to 3D scan, because as soon as you move the scanner to the other side of the trunk lid, you lose all of your reference geometry and it just kind of goes crazy. So even if you put 3D markers on the other side, it loses all the tracking of the geometry on the bottom. So you cross over to the top, you might get those markers, but it still doesn't have a reference point for how it lines up to the bottom of the trunk. So I'm also still trying to figure out how to get a good result from that. I do have a 3D model of the car separately. I might try to merge those meshes, the 3D model that I purchased of the car and the 3D models that I'm generating from the 3D scans. But we're just going to have to see, try a few things out, go through a little bit of trial and error. So I think I'll end this video here. We've covered quite a bit and made quite a bit of progress, so we will pick it up in the next one. Thank you guys for watching. Be sure to be kind to someone today, and I'll see you next time. Peace.